test is if you write out using KVL and KCL equations to describe the circuit, you end up with a second order differential equation. What you had last chapter was a first order differential equation, which you can just solve by finding an integral, and that's why you had all those integrals in this last chapter. Second order differential equations are a little bit more tricky to solve. And I'm going to start by looking at just one. So let's take a parallel. Do I want a parallel or do I want a series? I'll do a series because I'm only going to do one of these, and then after that I'll show you some shortcuts that we have, and then later on you're going to also see how you can use Laplace transforms to solve them even easier, which is why the DiffEq class spends so much time with Laplace transforms. Did you retake DiffEq? Okay, so I'm going to have to Laplace transforms probably sounds like I'm saying something.
In Calculus 3, we spent a little bit of time on Laplace transforms.
Okay.
To get through that stuff.
Okay, yeah, so I'll do, depending on which math class people take, you either do nothing but Laplace transforms, which I think is not good, or you don't do very much Laplace transforms, which is not good for engineers. But I'll make sure that you know enough for this class. We do that.
Okay.
All right, so let's take a look at this circuit, and let's do a KVL loop equation going around this loop. So the one thing that we do know is that we have our voltage across the capacitor is given as VC of t. So we're going to use that as our starting point. This is not on the handout. This is just the copy of the series RLC picture. Yeah, so this is not on the worksheet. So so we know that the voltage for the capacitor is VC of t. So if I do a KCL going around this direction, then I would get VC of t and then minus Vs. Now you'll notice Vs has the unit step function, so we're saying we just start it at 0. So before 0, it's 0, and that will allow us later on to solve our differential equations because it gives us a boundary condition. And then when we get to the resistor, it'll be IR, but this current, this is all in series, and so whatever current we have is the current through the capacitor. Now, we know that the voltage across an inductor, so VL, is L di dt. And so I can write, when I get to the inductor, I can write this as plus L dic dt. But my problem, and this has to equal 0, my problem is now I've got two functions in here, I have VC and I have IC. But that's okay. I know a relationship between those two. I know that IC is C dVC dt. So I can then write this as VC, and I'm just going to not put of t. We know that V now is a function. VC minus V, I'll take the VS to the other side. So VC plus C dVC dt plus, now I'm going to take the, write this next one in terms of VC, so it'll be L d dt of, now IC is C dV dt, and that all equals Vs. And so now when I take this derivative, that now we see where the second order comes from. So it's C dV dt plus LC d2v dt2 equals Vs. And then to get this in a standard form, I'll put a second derivative first, d2v dt2, and then I'll divide through by LC, plus 1 over L dVC dt, plus 1 over LC VC, these are all VCs now, equals Vs over LC. Which tells me I have a differential equation in the form VC double prime plus A VC prime plus B VC equals C, where A equals 1 over L, B equals 1 over LC, and C equals Vs over LC. And then you have all the methods that you learned in differential equations for solving this. And the different solutions depend on the relationships between these variables. I don't know if you remember or not, but when you did this in differential equations, you would look at your characteristic polynomial, which you would get by turning this into 1 plus AR plus BR squared. It doesn't matter if you remember, because you're not going to have to solve it that way here. Equals 0, and then you find out what the roots are, and if you have real roots, then you have solutions in the form of a to the minus ct, and if you have complex roots, you have a sine and a cosine. So anyway, so the only point of that was to show you that you get a second order differential equation that, as long as Vs is just a constant, it's not so bad. You know that you could solve this given enough time and your differential equations book, that you could figure it out. When Vs turns out to be a function and not necessarily just a constant, it could be a little bit harder. But what your textbook has done for you has broken it down so that you don't actually have to solve the differential equations. It has the solutions for you based on that you can just plug and play, except it's a lot of plugging, but it's still probably easier than making the mistakes like I would make to do it on my own. So like if you look at
It's formulaic. It's just like
it, yeah, it's formulaic. It's just, so this is the top of the second page of the worksheet. It shows you these are the differential equations that are being solved, and then this table shows you what the solutions are. And the bottom of the table, the auxiliary relations, are where you start. You start by finding alpha and omega naught, and then you figure out what kind of circuit you have and you plug it in.
She basically said to put this on your formula sheet for the next test.
Put this on your formula sheet. See, yeah, it's not worth it to try to derive them. It's not worth it. You don't get anything from that. But I do want to talk a little bit about alpha and omega naught before we actually practice solving them. So alpha is something called the damping factor, and it tells you a little bit about the behavior of your circuit. So let's say I'm charging a circuit. So I've got RLC charging. And this is the source, the voltage of my source. And I'm using series. It does the same for parallel, but with just series, I think is, for me, it's easier just to look at because it's just all in a row. So we would have close the switch at time t = 0. So we know eventually our voltage across the capacitor, so this will be Vc of t, our voltage across the capacitor is going to be Vs. Eventually it's going to get there. The values of R and L and C tell us how it's going to get there. So if I have a circuit that has the resonant frequency, so if omega naught equals 1 over the square root of LC, that's called the resonant frequency. That means that it's going to approach Vs in the smoothest, quickest sort of way. It's just going to approach it like that, exponentially approaching it, and we call that critically damped.
So critically damped is kind of like the standard case that you'd see, like most people draw.
That's what, yes, yeah, like it's what you would see in your physics books, yeah. And right, so that means you're at the resonant frequency. Now, if you are underdamped, what that means is you're going to overshoot. You're still going to approach that frequency, but you're going to oscillate above and below it. So you actually reach that Vs quicker, but you don't stay there. You overshoot and you come back. And if you remember, I said, some of your solutions to the differential equations can be exponential and some can be sines and cosines. And so these are just showing the different kinds. And so this one is called underdamped.
In class, we just understood it as the alpha is less than omega naught.
Yes, right. And I'm getting there. I just kind of wanted to show you what it meant in physical terms.
Yeah, I was just saying that I didn't understand what those meant. I just know the terms.
Yeah.
So, okay.
And then I'm going to do the alpha next. Yeah. Okay. And then you also have overdamped. And overdamped, it's if I just gave you this picture of the overdamped and didn't give you anything else on here, you'd be hard pressed to say whether it's overdamped or critically damped because you don't really know what the where VS is or whether or not that's the fastest way. But if you have given this information, it's easy to see that, okay, well, the one at the bottom is the overdamped one.
So overdamped means it's going to reach a value lower than Vs, that it approaches a value lower than Vs?
I think it still is going to approach VS. It's just not going to do it as quickly, as soon. I think that would have to be true. Let me see. Overdamped. It still is going to reach whatever VC at infinity is. Yeah, so it'll get there. Just slower. Did I print out my solutions? That's overdamped. And that is showing one that's charging. If you have one that's discharging, you have similar sort of stuff. You'd have, let me see if I have a graph. No, I don't have a graph. Okay. Okay, now let's say we were discharging. So we're starting at some value. And I'll put my 0, so this is 0 volts. This is V. Just V naught where it's starting. This is the voltage across the capacitor. So if I have critically damped, it's going to exponentially decay and approach 0. Or if it's not approaching 0, it's approaching V infinity, whatever V infinity might be. Like if you had a source, another source in your circuit, and so it was not going to 0, but was going to something else. So that would be critically damped. If you have underdamped, just like with the charging, it's going to overshoot and then oscillate.
Because it keeps overshooting.
Yep, it keeps overshooting. So it goes too far, and then it goes up too far, up too far, up too far. And then underdamped just means it's not doing it as well. And if you look at your solutions on that page that has all the solutions, if you see the underdamped solutions are the ones that are combinations of sine and cosine, and the critically damped and overdamped are both exponential functions. It's just the overdamped is a combination of two different exponentials, whereas the critically damped is one e. So the critically damped is e to the minus alpha t is the main part of it. And then the overdamped is e to the s1t plus e to the s2t with a bunch of other constants thrown in there. And so the critically damped gets the one exponential that just gets it there quickly. Okay, so I talked about the resonant frequency, and I gave you what I said was the resonant frequency for series. It turns out it's also the resonant frequency for parallel. So that's nice. So if you have an RLC circuit, the resonant frequency is 1 over the square root of LC. Now, the damping coefficient is different for the two different types. So the damping coefficient, alpha, is R over 2L for series and 1 over 2RC for parallel. And I don't have any tricks for remembering it because I don't remember it. I have a formula sheet. And it's alpha, and alpha has these strange units called nepers per second. And a neper is like a decibel or a bell in that it is a unit that doesn't have units. It's really a ratio of two things. At this stage, it's not important to understand what it is, but I thought just in case you are curious, what kind of units is that? A neper is showing the relationship between two different things. Like a decibel is another example of that. So when we talk about decibels, usually you think sound, and really what it is it's the logarithm of the ratio of a sound to the threshold of the limit of human hearing. And so you have this, like, a set number, a set value that you're comparing it to, and it's a ratio. So
It's a ratio?
it's a neper is actually 1. So it's like, well, why do you even have it in there? So you don't have to if you don't want to. You could just say per second.
Oh, really?
Yeah.
Per second is really just per second?
Yeah. Because the neper itself is a ratio of two identical units, like volts over volts or current over current.
Weird.
It is weird. Okay, and then you use this alpha, as you already know. If alpha is greater than omega naught, then it's overdamped. And alpha less than omega naught is underdamped.
So per second is a frequency?
Yes. Yes.
So the frequency is larger than omega naught frequency?
Exactly. And then omega naught is a frequency, and it's an angular frequency, and so this can help you remember if my alpha, which is some sort of frequency, is greater than my omega naught, my critical frequency. Okay, that's overdamped. So that can help you remember which way is which. Is that the omega naught? You have to remember omega naught is your critical or your resonant frequency. And so once you have that, then you're good. So this is critically damped. All right, well, let's do a problem. So probably, what time is it? Yeah, we probably will get through one. These take a long time. But I'll try to do one of each type before exam time. So I believe the first one is... Actually, let me stop this and save it. It's just kind of like my introduction. And then